Next up is Shoaib from Esper. I'll give him a round of applause. Thank you. I'll just put this on you somewhere. Yep, so that's it. Okay.
Yeah, let me get on that. Ooh, there we go. Alrighties. Well, hey everyone. Sorry, I was a little bit late showing up, so I couldn't really socialize at the start. But yeah, I'm Shoaib. I'm from Esper Satellite Imagery, and well, as it says, we're a company that's trying to save the planet through data. Basically, what we do, or I guess what we're looking to do, is I forgot to we are so. This sort of goes back to how in prehistoric days, we used to look at the skies, we used to look at the stars and use that for navigation, for weather forecasting, and basically, using the stars to guide a lot of our principles as human beings. So we're doing something similar, but now in terms of using, I guess, the stars or space in general to sort of look at more challenges that are facing the Earth, more from a climate perspective. So essentially, we are building hardware, launching it up into space, and using that to track climate metrics, climate data, for very specific industries. Again, just waiting for the slide to change. But while it does, we're looking at everything from resource management all the way to everything like forestry and agriculture. So some of the things that we're looking at are methane leakages. So oil and gas companies, coal mining, and a lot of these things, they release a lot of methane from everything from whether it be the pipeline that's carrying it, because methane is still a natural resource. It's natural gas. We use it for our homes. We use it to basically stay toasty. But it still is also, around 80 to 90 times a lot more potent than carbon dioxide. So which means that it traps a lot more heat than carbon dioxide, making it, again, a deadly greenhouse gas. So we're looking, then beyond that as well, we're looking at mineral exploration. So mining, has this entire area around it where, we know that there is a huge environmental impact of it on the planet. But then we are also reliant on it more than any other resource-focused industry, minus agriculture. We need, mines. We need mines to, get our iron, get our steel, get the stuff that goes into our electronics, into our batteries. And mining is basically what's really powering the next gen green tech movement. Everything from new battery technologies all the way to electric cars, all the way to more efficient building practices and just sustainable infrastructure in general. A third area that we're looking at is more along the forestry / agricultural side, where we're looking at carbon capture. So instead of instead of helping other industries be a lot more efficient, this is where we're directly making an impact in terms of carbon reduce in the actual atmosphere. So we're helping track carbon that is sequestered by forests, by coastal areas through seaweed, and basically agricultural land as well, where farmers and forestry reserves, all the way to farmers of seaweed, actually get paid out to plant a lot more crop to actually capture a lot of carbon from the atmosphere. And we're building the data systems to be verifying a lot of that, to actually have a proper, a more positive impact on the environment by helping reduce carbon dioxide in the actual atmosphere. The way we're doing that is we're building and launching satellites into orbit that can track all of these chemical metrics. So we're building hyperspectral sensors. So these are sensors that they capture light in hundreds of different wavelengths. So not to get all physics on you, but we're basically doing spectroscopy on a macro scale of the entire planet. So we're capturing light in hundreds of these wavelengths deeper into the infrared range. We're utilizing all of this information to look at chemical absorptions and reflectances. So every mineral, every material reflects and absorbs light differently. We're basically able to look at the entire spectrum. We look at where it's absorbing, where it's reflecting, and basically look at its spectral fingerprint. So spectroscopy is fairly commonly used in a very small lab environment, but now we're doing that for the entire planet on basically a square kilometer level. Everything from the columns of the atmosphere to surface level data. So we've been working on this stuff for the past 4 years now. Started it off as a university side project. It was just me and my co-founder. We met in our first year of our engineering degree. In our second year of our engineering degree, we ended up going to a hackathon which we ended up winning. That's how we sort of, got into hyperspectral tech, and this is actually one of our first prototypes that we built. So we took his dad's DSLR camera, put this entire, so there's like a bunch of PVC pipes here, a couple of off-the-shelf Canon lenses, and basically for the first lens, we capture a lot of light in, we focus it onto a diffraction grating. Essentially, it's a prism. It's the same concept as a prism, but it's a film. We focus it through that, and there's, goes through another PVC pipe to, again, go through the main actual imaging lens or a proper camera lens to basically look at these really fun rainbows that we end up capturing. So on the right is also like the first hyperspectral image that we caught. It was just a banana taped to a door. We were trying to get creative. Instead of taking pictures of fruit baskets, we were like, yeah, let's just tape a banana to a door. So we sort of built our first few sensors around the same concept. It was still a university side project. We were just working on fun. And hopefully trying to see where it goes as a business, and we're looking at a lot of business cases. So we were at Monash at the time. I think this was while we were at our second year of engineering degree. Was it third? Yeah, it was probably third. And that's how we sort of graduated to working in, as a side project to working on it full time, but outside of Joey's kitchen. He's my co-founder. So that's us building our second sensor again on his kitchen countertop. So similar concept, we just made it a lot smaller so it could fit inside of a 3D satellite, 3D CubeSat. That was us still sort of working out what we eventually wanted to do, as we were still, playing around with the technology, but just because we thought it was cool and it was fairly accessible, at least the way we started engineering it. So we worked on this prototype for a bit. That's around the time that we raised our first bit of funding, mostly family and friends. Then we ended up getting a manufacturing grant from the Israeli government as well. That's when we really got around the business cases that we actually want to be focusing on, rather than just building cool cameras and launching them into space. Now here's a few pictures of cool cameras that we'll be launching into space. So graduating from that first or that second iteration of that sensor, we've been building our first space rated module. So completely strays away from the initial philosophies or engineering philosophies that we're really looking at from the first few prototypes. We designed this from the ground up to be surviving the space environment. So everything from aerospace grade materials to internally, we were still using a lot of off-the-shelf optics to be developing that entire, focusing optics to the prism optics, then focusing it again on essentially an image sensor. And yeah, that's basically what this sensor essentially does. So these two images are from our space qualification test. The one on the left is from our thermal vacuum test. So right behind that, you'll see this entire stack of computers that we have there. So we're working with a company called Spiral Blue. Some of you guys might have heard of them. They make space edge computers. So these are computers specifically for payloads like ours, for Earth observation payloads. And we're using them to do all sorts of like software stuff on the actual sensor data that's coming out before we actually downlink it, just because it's, tons of data that we're generating, because we're capturing hundreds of wavelengths instead of just 3, which you would be normally doing with like a normal RGB camera. So we're using their platform to do everything from payload control all the way to doing a lot of onboard analysis. So what I mean by that analysis is that when you capture images of the Earth, around 40% of the Earth is always covered in clouds. And if you're in the visual spectrum, which these sensors currently are, that's basically useless information. You don't want to be downlinked to that, because then again, that becomes a cost to running the actual satellite up there. So what we eventually end up doing is run the algorithms to look for clouded images and delete them, just because we know they're not that useful. The image on the right is us doing the vibration testing of the actual thing. So again, making sure it survives the actual launch environment. Same thing was with the TVAC testing as well. So these are fairly recent photos. So our TVAC testing last December, and the vibration test was I think 2 months ago now. last week, we delivered the first sensor to our launch provider. So we're launching on 2 satellites this year. One's going up in October, and the second one is going up in January. So we delivered to the January launch before we did for our October launch, which is weird. Yeah, this is the actual sensor inside of the actual compartment we will be in when we're on the satellite. So it's basically a 3U CubeSat deployer, which is now being repurposed as like an entire hosted payloads compartment. So for those who don't know what hosted payloads are, we basically, as a payload, we buy space on other people's satellites. They give us everything from whether it be logistics to the launch logistics, all the way to all I guess the in-space logistics we need to actually get the data down off our sensors once they're actually out there and capturing. So that's what we're doing for our January launch. The second launch, however, is a more dedicated satellite. I don't have a picture of it, but I do have it on the back of my hoodie. Yeah, I love this merch. So that's the satellite we're flying on in October. So that's an entire 30U satellite. So basically, yeah, it's a little bit smaller than a mini fridge. And that's a completely dedicated mission for us. Launching in October on board an Esper rocket. This payload's going up on a SpaceX rocket. Essentially, it's fairly cool imaging technology that we're building and launching. But a lot of what we're still focusing on while we're building cool hardware is still looking at a lot of the climate problems that we're working with. So everything from carbon sequestration to carbon monitoring, and I guess mining sustainability is a really huge pillar that we've based a lot of our technology around, just because that's being local in Australia, that's around 30% of our exports, and that is just a really closer story to us. Especially as we sort of get deeper into, I guess, the developments that are happening in climate tech, they all rely on critical minerals and all the technology that's coming from that. And we want to be an enabling technology to basically make that entire supply chain as sustainable as it can be. So yeah, that's sort of about us. I feel like I rambled a little bit here and there, but yeah, just wanted to show you guys a few cool pictures of the stuff that we're working on. I'm happy to sort of dive into different parts of whatever you guys find interesting. Yeah.
You do any I assume you sell that data?
Yes, we do.
Do you do any pre-processing, or do you just raw data?
Yeah, so we are primarily positioning ourselves to give the raw information available, but we still do some pre-processing on the actual data. So to take a step back, like the raw sensor information that we capture is not something that you can plug into some GIS program, or have somebody look at it and be like, oh yeah, here's carbon or here's XYZ, right? There needs to be a lot of work to be done on the data before it's even like ingestible, even by a software program, let alone our own eyes. So we do some of that ourselves. So everything from making sure all the data looks clean, because we're capturing it from space. There might be radiometric corrections. Sun might be too bright that day, which means that we need to account for that and reduce the brightness of our images and do a lot of those corrections, and geometrically as well. Let's say if because we won't be always looking straight down at the Earth, we might be looking at some different angles. That might mean that some pixels might be further away from the actual camera than some other pixels, so we need to correct for a lot of those things. So that's a lot of the processing that we do in-house to actually make it something that a company can buy and start ingesting into their own data systems without doing a lot of that stuff, because that is again very specific to us knowing all the telemetry data of, I guess, what we're working at, of the actual sensor and where it was in orbit.
Do you need to qualify that data and ratings?
We do. So essentially that happens in like the first 2 months of the actual satellite launching. So we do calibration of it in orbit. There are, I guess, different sites across the globe or control points essentially, which have a known spectral radiance, and depending on different orbit altitudes and those sort of things. So we know if we look at it, what we're expecting to get, and versus when we look at our own data, we can tune it and calibrate it to actually capturing, I guess, spectrally accurate data. Of course, we do a lot of the calibration on the ground before we actually set it up, but that's the in-orbit calibration is probably the most important step when it actually comes to making sure our data is spectrally accurate, and from a geo point as well. Those are, I guess, the control points that we use. It really gets hard when we're capturing over oceans because, well, oceans are flat, plain, unless you're just looking at waves, right? So it's really hard to determine between different images and where different points are. What we're thinking of doing is capturing a ton of data from one shore to the other shore, and then using those shores as control points to, I guess, make the entire data strip that we're essentially capturing basically geo-rectified. Planet Labs does this, and for us it might be a really big stress just because, again, we're capturing 100 times that information. So we're looking to figure out better ways of doing that, but for now that's the only solution that I guess the industry knows of.
What's that area?
Yeah. So we are a push broom sensor, so that essentially makes us a line scanner. So per each capture, it's different. Width-wise, though, we're capturing like 8.5 kilometers. So it's fairly narrow compared to what's already out there. Like I think Landsat and a few of the satellites are like 15 to like 20 kilometers in their entire width. That they end up capturing, we're only 8.5. Again, it's a smaller sensor. We're trying to pack a whole lot of technology in there. We're capturing like 100 different wavelengths from visual to like touching near infrared. So for this size sensor and I guess with the quality of data we're actually capturing for the cost, it's I guess we've packed a little bit too much in there, which we're trying to work around.
I have two questions. The first one is capturing 100 times a day. What's the effect of time capturing process? I guess like you have to think about that.
Yes. So it really limits so that means we can only task the images. We can only tell it what to capture instead of always be capturing. So ideally we want to be, always be capturing the Earth, monitor every single point on it, even if there's nothing happening. But because again, we're generating all of this data, which is, putting a whole lot of cost on the actual, obviously from a monetary cost, but also a hardware cost because it's taking up all that bandwidth. It really makes us pick and choose areas where a customer is actually paying for that. So yeah, while we want to be capturing the entire Earth, and hopefully we'll get there one day, and that's what we're working towards from a huge computing point of view. But for now, it's just we need to be told where to capture, when to capture, and that really, I guess, and that's again, the customer is limited in some sense because we need multiple satellites up there to be doing very broad scale captures at fairly frequent intervals. And that also puts again strain on us where we're using up a lot of the bandwidth that's available to us up there.
You briefly, like in 2 slides, you went from this really cool looking prototype on a kitchen bench. I'm doing a flight test on an optical sensor that's going to space. There's a lot more to that story. Do you want us to talk a little bit about like what you had to learn and figure out?
Absolutely.
That's
Absolutely. Let me actually good point. Yeah. So funny thing we learned is Canon lenses do not survive in space. Yeah. So I was surprised. So there's when putting things in space, especially when working around with optics, there's a huge concern around outgassing of different elements of the actual system. So that because essentially if you fog up your lens, the data you end up capturing is useless. You spend hundreds of thousands of dollars developing this payload, and it eventually ends up being again useless. So going from I guess our second prototype that we were building, we were still using a lot of off-the-shelf equipment, everything from again these Canon lenses and stuff that worked great because we didn't have to engineer our entire optical system around that, and we're working off of these lenses that basically correct all the images for us as we could end up capturing. Once we sort of moved to space, we can't really use any of them. We had to completely scrap the design that we were working on, that we basically worked on for a year and a half, in favor of the actual space grade design. So again, going to the spectrometer physics, we were still looking at a lot of the same, I guess, principles. But we ended up having to completely scrap a lot of the parts that we were using, a lot of the engineering effort that we went into it, and in some ways completely start from scratch. So we had to, first of all, we had to like select materials that would actually, from an optics point of view, that would, work in space and actually capture good data. And that's how we started, doing a whole lot of simulation. It started with a bit of simulations where we were like, all right, there's 100 of these spectrometer concepts out there. We worked with a few of them, and we basically started simulating, all right, what is, gives us the best data quality for, I guess, stuff that's available to us on hand. Because we still had a very limited budget because we were still at uni while we were building these. So under a few $100,000, while paying the entirety of our staff, how do we develop a space grade sensor with which does a lot more than what any other sensor of this size has done, while staying under that budget, and that was like one of our biggest engineering challenges. But that's of course now become a huge competitive advantage for us as well. One of these sensors, while it's space rated and it's capturing so much more data, it only costs us like $20,000 for us to build. So that's on a grade of like a space hardware that we can build one of these every 6 weeks and launch these for like a few $1,000s on top of that, a few $100,000 on top of that. But yeah, one of these like hardware articles like really costs us a lot, a very less amount of money to actually get these things up into an orbital condition. Yeah, it was completely going back to the drawing board and starting. All right, we know how the technology should work. Now it's like, let's start this from scratch. So technically, this is V1 in all spiritually V1, even though we've learned from the first two prototypes. Yeah.
What is like different from your competitive labs? So like one that's sales are about micro satellite. What is like some of the better capabilities?
Yeah, so again, Planet Labs, they're primarily focused on capturing color imagery. So they're looking at objects. We're looking at what those objects are made out of. So we're looking at more on the chemical data side of I've been doing a lot of that chemical analysis. There are a lot of overlapping use cases, especially within agriculture, because they're also red, blue, green, and a little bit of infrared. So they get a few indices that we're also capturing. But then, of course, we go much beyond that in the sense of instead of being able to tell, oh, hey, here's dry pasture because it's yellow, not green, we're able to tell, all right, here's this X amount of protein in your crop versus Y amount of nitrogen or potassium in the actual soil. So that just goes into a very, because it's still a different application. We're not like competing with them. It doesn't like, there's still a huge need for a lot of that data. But yeah, once we sort of go into that, entirely differently new use cases come into play. Planet Labs is launching their own hyperspectral sensors as well. They're launching 2 later this year, so we might be launching on the same rockets. Who knows? It'll be cool if it does happen. But yeah, those sensors are they do kind of like throw us out of the water. But I guess looking at costs, that does cost them like tens of millions of dollars to build, and this is like a $15,000 thing. Yeah.
So just getting it right, hyperspectral online, so like taking kind of wavelengths of like video like figure out spectrums, kind of like things you have to take into account.
Absolutely.
Maybe like just track from the ground.
That's right. Yes. Yeah. So especially when it comes to like atmospheric level data, like gases and all those sort of things, the ground is of course going to be a lot more brighter and a lot more prominent what we're capturing compared to like just looking at entire columns of atmosphere. And once we of course look at entire columns of atmosphere, different gases have different densities. They'll be their spectral signatures will be mixing in together. So there's like, we're not building the data science ourselves to actually do a lot of that processing. We're still, working with our customers and working with, I guess, other sciences institutes to actually build a lot of that out with our data, which is why I'm like, let's just build the hardware and put it up there, because that is still easier than building that data science. So yeah, we're taking the easier end of the stick. But yeah, yes.
So you have customers.
Yes, we do. We've like an entire pipeline of 150 mil in pre-orders that we've accumulated. So yeah, once our sensors start going out, they're already like almost fully booked out. We still keep like capacity available.
Of the phenomenon, is there any that you actually I'm thinking things like with, is there any other agricultural
Yeah, so with this current sensor, not many. But we are, again, as I mentioned, we're really expanding deeper into the infrared range, going into short-wave infrared, which is like 2,200 nanometers. That's when a lot of possibilities really become available, just because, first of all, a lot of that data has not been available, especially in the spectral resolution that we're going at. So even there's a lot of applications that are there are not known because the data hasn't been available to conduct a lot of that research on. Secondly, in a lot of the stuff that I mentioned in terms of the applications that we're currently looking at, that's our focus for now. Mainly because once we start going into, I guess, more blue sky is type of things where it's like newer applications that are coming up, that becomes on us as a business. It just becomes a lot harder for us to do while building these sensors. And again, goes more down that data science route where we're like, yeah, again, it's us being hardware engineers, that was too hard of a problem for us to look at. However, we are looking at a lot of interesting things with, again, working with our customers there. So micro macronutrients for agriculture, where I mentioned the protein, the crop, all the way to ground level nutrition. That's something that's fairly new in the precision agricultural industry. So that basically, when maybe not from a farmer's point of view, but let's say if you're a futures trader or a commodity trader, this goes beyond just yield prediction because you're now able to look at entire nutrition that a crop has versus a different crop in a completely different region. So that's at least something that comes to mind in terms of just, I guess, envelope pushing applications that we're looking at. But yeah, there's a lot more that we're hoping come out of it, and that's basically our bets. Once we sort of make this data a lot more available, we're betting that there's a lot more applications coming out of it that we just don't know of yet.
And don't get me wrong, I'm all for this, but is there like an element of data privacy to this? Like you're imaging everyone else as well. Is that right, or is there around that?
It is definitely something to think about. However, there are, I guess, limitations in terms of how much we can do. For example, let's say a commodity trader is going to be paying us a few $100,000 to go out and capture all the farms of, let's say, Victoria, for example, that will be shedding light on few properties or few farmers that they might not be doing so well, and that is, of course, their data that's being given out in a sense publicly because anyone with enough money can actually go out and buy it. There's not a whole lot we can do there in terms of actually regulating it unless we go out and audit every farmer that's there or every person that's being impacted by that data. There are a lot of implications when it's from a defense perspective. For example, we can't capture imagery over the US or downlink it unless we get a license from NOAA. They be like, yeah, we can capture our geospatial land. And a few other countries do have similar things like that. Australia doesn't, so any satellite going over Australia can capture and downlink, and there's no regulation around that just yet, unless stuff that's been talked about and that's slowly coming to play, but nothing that's a law just yet. So yeah, for us, it just becomes a thing of good faith where we're just like, is our customer going to use this data for bad or for good? And that is something that's on us, and that's something we have to verify anyway, because we don't want hostile entities to be essentially just because they have money they don't. It doesn't mean that we have to give access to them, access to our satellites to them. So that's a process that we have to do anyway, and that's something that we're looking to implement a lot of these other ethics into that too. But yeah, being honest, we're still fairly early before we get to that point, but we are thinking about it. Yeah, so pre-orders, so because again, we're cheaper, that allows us to look at customers who are capturing very large land masses. So if you go out and buy a similar data image, it'll cost you like $30 per square kilometer, not assuming there's a minimum order quantity on it. If you're a customer who's looking at millions of square kilometers, that $30 per square kilometer really scales up, because we're 20 times less. We're offering $1.50 per square kilometer. That just allows us to go for these really large customer sizes. And that's how, if we get 10 of them who are buying millions of these, that's how it sort of really adds up to that entire pre-order book, even though we're still pre-launch fairly early in our I guess, technical / product life cycle. That's just allowed, I guess, again, engineering it from the ground up, working with those initial problems really helped us get to where we are. It was pretty much accidental, but we're happy we're here.
The good sensors you have on the data processing, are you measure data or get measurements at various depths from the about that? So it looks like it's essentially
We are surface level, so it is surface level reflectances depending on the soil types, depending on the clay types, or whatever we're capturing. We might be able to penetrate around 15 centimeters of it. I guess the 15 centimeters mostly comes from like agricultural porous soil. I'm simplifying quite a few things here, but that's sort of different topographies will have different depths. But for all purposes, we're basically surface level, which is why it's surface level of the Earth all the way to the atmospheric column until it reaches our sensor.
and sorry, I have a follow-up. And do you have, I guess, like the sensor targeting sort of do you have like some free time where experts is capturing data of becoming to your own customers? If so, do you plan to like, are you like thinking about the like of open that data, having like other people look at it, like that data?
Yes, absolutely. So at least with these two, of the first two sensors, we are primarily looking to do that because we don't have a whole, I guess, because there are first two, the data might be really bad, or it might be what we expect it to be. So a lot of that data will be sort of given out fairly openly. That's what we're planning to do with these first two, and in ourselves, we have to conduct our internal technical audits as well to be like, all right, if we're especially when against going back to that calibration piece, where you have to capture our own data. I do see ourselves playing a part when it comes to, I guess, open source intelligence. I do see us sort of capturing a lot of data and sort of making it available there. But there is a huge cost constraint, and there's that entire processing constraint that would eventually become a decision of like, hey, do we capture this for an open source use, or do we have this customer who wants to buy it instead? So it would I guess be a decision for then. But yeah, that's sort of like a dilemma that we I guess do sort of face there.
These will be like episode. What the problem is the last question I'm asking. You mentioned that there is some amount of regulation around capturing data. Out of curiosity, and how would the US government regulate or prevent you from
Yeah, they cannot in some purposes, but the U.S. Department of Defense is again the biggest buyer of satellite imagery data. Even if we're not a U.S. company, they're still going to end up being our biggest customer, even while we're focusing more commercial use cases rather than defense and some of the use cases. It is unfortunately a bit of an eventuality, at least in the short term. At least in the next 5 years, they're still going to be one of the big buyers of that data. So of course, we wouldn't want to do anything to step on their toes. Yeah. For sure.
Okay.
All right, I think we should probably sort of wrap it up there. Thanks.
No problem. Thanks a lot.